We're going to get started with the presentation today. So if we can get that up on the screen.
I think if you hit the button mark.
Oh, will it just take me there? Oh, there we go. I'm Mark Wagner, and I'm with the I4C, which is one of the 10 Martin Delaney collaboratories that focuses on HIV cure research, and it is immunotherapy for an HIV cure. The background are neurons, because I also work on the effects of HIV on the central nervous system, like the brain, so that's why I chose that background. What I'm going to talk to you today about is why HIV is so hard to cure in a nutshell. If somebody is on antiretroviral therapy and the virus is suppressed to undetectable, which, as we know, undetectable means untransmittable, there are very few cells that actually harbor HIV that could be what we call the reservoir, where if antiretroviral therapy is stopped, could start with the replication of the virus beyond that. So you can see in this field of tulips, there's only one out of the vastness of all the tulips. It gives you some idea of how there may be one, and all it is one minor change. And because it's not producing virus, the body itself doesn't know that it's different. So it still looks like the others, it's just a little bit different. On the right is a schematic of an HIV virus. HIV itself is not living. It only lives if once it enters into the cell and takes advantage of what the cell has to offer. I consider the cell, which is on the left, a kind of mini-me, because the plasma membrane, I think of that as the skin that's on my body. And inside there, you see there's things like Golgi bodies and mitochondria. They're like organs, like you have a heart, lung, things like that. And inside the middle of the cell is the nucleus. And, I consider that more like the brain. It kind of drives everything. So if you think of it that way, it gives you some clarity. But inside that nucleus is the genetic information that decides what that cell is going to be and what that cell is going to do. And that genetic information translates into a blueprint, basically. And what HIV does is it's able to put its blueprint into the DNA that's there of that cell. That's what makes it so challenging to cure HIV, is because it actually becomes part of that cell's blueprint. So then it can, in the future, if the situations are right, produce more virus. And I like the analogy of a dandelion because, as you see, there are different stages of a dandelion. You have the bud and you have the flower. Those really aren't a problem. But when you get to the seeding part of the dandelion, we know what comes after that. And when you get a good gust of wind, then those seeds just go everywhere. So, and when those seeds, in which they're not living yet, but when they touch ground and they are given water, they will give rise to another dandelion. But, the interesting fun fact about dandelions, because I researched this, is that they can live for 14 years if they're undisturbed. That means if you haven't treated your lawn to kill them, or you haven't tried to dig them out or anything like that, they could live for 14 years. The same thing is with the cells that have, the few cells that have HIV in them. They can live up to 40 years. So that makes it an additional challenge for us as researchers to cure HIV. And here's showing what happens where if someone's not on antiretroviral therapy, HIV is able to enter into the cell, and then it's able to make more of itself, and then it spews it out just like a dandelion. So then these little viruses can go out, and if they come in contact with a cell that is receptive and able to allow that virus to enter, which, thank God, HIV does not enter into every cell, because it would be in real big trouble if it was able to do that. But it's the same type of system as you would see with the dandelion. And getting back to this is where, that one cell. So our challenge is, how can we disturb that one cell out of all those others so that they would become visible to the immune system, so the immune system would be able to take care of that. So as long as it's not making virus, the body doesn't know that that cell has a problem. So if we can disturb it, much like if we were treating the lawn for dandelions or digging it up, then we could possibly win and cure someone naturally with HIV using a vast array of different modalities. And we'll go into some of those. One thing we're now 40 plus years into the HIV pandemic. And I know a lot of people, I've been living with it for 39 plus years, it can seem frustrating. We're this far into it and we still haven't cured it. Why not? But literally for hepatitis C, it took 25 years from discovery to cure. So, I want to say that there's always hope. So it just means that we just haven't figured out how to do it yet. But there's a lot of people working on it. Now this introductory module that I'm pulling some of these slides from was a collaboratory effort that is actually on the Treatment Action Group website. So I recommend, if you want to learn more about HIV cure research and all the different things that you'll see here today, that if you go to the Treatment Action Group website and look up the curriculum, which you see in the far lower right, you'll be able to see that massive effort that we did as a community effort. So what does a cure mean? Well, it means free of symptoms, off medications, you can't transmit virus, you're no longer contagious. Pathogen is cleared from the body, meaning it's no longer there. And reduced healthcare costs. With evidence, we were discussing some of this just a little earlier. A lot of the cures to date have been through bone marrow transplantation, but not all. And the transplantations were done by donors that had a natural resistance to HIV. That meant that they lacked one of the doorways by which HIV must enter in order to become part of that cell and continue the cycle of HIV. But this isn't scalable, nor is it safe to do that. But it is proof of concept that yes, we can cure. So it's been the impotence of all the work that we will see coming up in the efforts beyond that. There are post-treatment controllers. Finding out your status early and getting on treatment earlier has benefit. It can create post-treatment controllers, meaning that the amount of cells that might be your reservoir or actually have that blueprint of HIV in them will become less. So it's really important that you learn of your status early, and if so, get on treatment so that you have the possibility of having less problems from it. Now we're going to go through some of the strategies. There's early antiretroviral therapy, to reduce the reservoirs. You can make the cells resistant to HIV. That's going to be through gene editing, or in this case, the bone marrow transplantation obviously did that. Deplete the cells that have the blueprint of HIV in it. So finding some mechanism by which we can make them come out of hiding, and flush the latent reservoir, and that's another way of getting it to be recognized by the immune system. Vaccines and immunotherapy, these are all ways that we can harness with our immune system, which is it is such an amazing organ of lots of cells that really help us in fighting all kinds of pathogens, whether it be a cold or anything. The symptoms you have when you get sick with a cold is because you're fighting it. Your body is making something to fight it. So we're thinking of ways of how we can use those things that your body naturally makes to possibly help us in the fight against HIV. Latency reversal agents are agents that just take that cell that has the blueprint of HIV in it and allows a way to possibly wake it up, and by doing so it'll start to make virus, and then the immune system will say, oh yeah, that cell is bad, we need to get rid of it, and it will cause cell death and eliminate it. If we can do enough of that, we can potentially clear out those very few events of cells that would be present that will keep the virus alive potentially in you. And this is just a blowhorn waking it up, so it's just a cute schematic. Cell and gene editing, this is where you use some other tool to go into the brain of the cell, that nucleus that has the blueprint of HIV, and actually remove either HIV or edit in such a way that the cells become resistant. Because one of the doorways that HIV enters, if you remove that, then HIV can no longer enter into the cell. There's immune-based therapies, antibodies. We've heard a lot about antibodies from, especially with COVID. People early on were being treated with antibodies from people who recovered from COVID because they didn't have any other way to treat them. Quite frankly, they did the exact same thing with HIV, because when I became positive with HIV back in the early 80s, I ended up going to England, and while I was there, because I found out probably 3 months before I went to England that I had HIV, so I was staying with my brother there. I went to Cambridge, and they drew my blood, and they found that I had a lot of antibodies. So I would go weekly into Cambridge, and they would take my blood out, my plasma, and use that to treat other HIV, people living with HIV over there. But obviously that wasn't sufficient. There's other immune vaccines, the DNA and the RNA ones that we hear about with COVID can also be employed here. Viral vectors. The first COVID vaccine I got was the AstraZeneca one, where they used the chimpanzee adenovirus vector, and that delivered the information so that it would make the spike protein, so that my immune system would make antibodies against that. There are protein and peptide vaccines, so they're just ways of, what it is that you want to target, and you give that. And then there's actually dendritic cells, and that's a really highly specialized immune cell, but it's really important in presenting antigens to other immune cells to help it to fight infections. So there's ways now that even some of that is being used as well. The I4C focus is on immune approaches, and that's the group that I'm with. And all these cells are your white blood cells, and all of them are extremely important. neutrophils, eosinophils, basophils, monocytes, T cells, B cells, natural killer cells, and macrophages. T cells, can be broken down, into T cells, or can either be CD4 or CD8. The CD4 cells, if you get a CD4 count, those are the cells that are predominantly susceptible to HIV. The CD8 cells are considered cytotoxic T cells, and they actually are part of the cells that would be killing the cells that would be infected with HIV, as well as natural killer cells. They're able to deliver a lethal dose to either be a cancer cell or a virus, cell with virus in it, to be able to help eliminate it. So these are ones that we predominantly focus on within the I4C. And who knows? All these approaches may need to be combined together. So, it may be that we need to take a number of these, bring them together at the end to give the most desirable result that we want. We won't know that until we study everything and begin to put it together. And there's even block and lock. Block and lock is where you take, because remember, HIV puts its blueprint inside the cell. So there's a way that we can possibly lock it up so that it won't be able to make more virus. So if we can do that, then someone can live without needing to take daily medication, and the virus won't be a problem, because if it's silent, it's not a problem. I was really privileged to be a part of the development of the introductory module, but there's many other modules of this program that is on the Treatment Action Group website. So I highly recommend, if you want to learn about all the different aspects around HIV cure research in detail, you can download the PDFs or the PowerPoints. They can be used by anybody. We put this effort together so that everybody can learn more about HIV and HIV cure research. And then, that's it. Thank you.